In this section, we will look at conservation of momentum. Let's first review that the Newton's second law version in terms of momentum is that the net force is equal to the derivative of momentum with respect to time. Alright, so let's consider a collision in 1D between two objects. The objects are approaching each other at velocities in different directions. They collide and then they'll move off at different final velocities. During the collision, Newton's third law tells us that the forces acting on each object are equal and opposite, and no other forces act on the objects during this collision. So let's add up the derivative of momentum, or the net force, for each object during the collision. So we have the net force on object 1 plus the net force on object 2. Now, due to interaction forces, we know that these are equal and opposite. So we'll have negative F2 on 1 plus F2 on 1. So you could write this as F1 on 2, and it would mean the same thing. Okay, so adding those, we get 0 since those forces are equal and opposite. This means that we have this set of derivatives must add to 0. And we can pull out d by dt to take the derivative of the sum, which means that what's inside, if the derivative of it equals 0, it must be a constant. So this tells us that the sum of the momentum of object 1 plus the momentum of object 2 has to be constant. So we can apply this to before and after the collision, and this is the law of conservation of momentum. So I'll just write it in another way. The law of conservation of momentum it says that the total initial momentum of a system equals the total final momentum. And this is for isolated systems. So in an isolated system, momentum is conserved. Now we can have momentum conserved in non-isolated systems if the external forces do not change the overall momentum of the system. And often this will happen if gravity and the normal force are acting on a system that undergoes a collision, but they're balanced. Then they don't change the momentum or the speed of either of the objects. So in this case, remember that momentum is a vector. So if we want to calculate the total momentum of a system, then we're going to need to add up momentum terms for each object and do that using vector addition. So our total momentum of a system would equal the sum of all the individual momentums for each object. So for example, P1, say P1I plus P2I, and so on. And we can take the sum of the momentum of all of the objects before the collision and after the collision, and they must be equal if it's an isolated system. So let's look at the first example. Kilogram archer stands at rest on frictionless ice and fires a 0.5 kilogram arrow horizontally at 50 meters per second. With what velocity does the archer move across the ice after firing the arrow? Okay, so I'll let 1 be the archer and subscript 2 be the arrow. And we have total initial momentum equals total final momentum. And in each case, we need to separate this to have a term for the archer and the arrow. So we have P1I plus P2I equals P1F plus P2F, and we can plug in mass times velocity for each of those momentum terms. Now before the archer fires the arrow, both are at rest on the ice. So we have 0 initial momentum for each object, and the total initial momentum is 0. So plugging that in, we can then solve for the velocity of the archer after he fires the arrow. So we have negative m2 v2f over m1, and then plugging that in, negative 0.5 kilograms, 50 meters per second. I've chosen the arrow to go off in the positive direction, over 60 kilograms. And then we get negative 0.417 meters per second. And notice we do get negative to show us that the archer moves off in the opposite direction from which the arrow was fired. So before we do some more examples, I want to go over 3 types of collisions. The first is an elastic collision. An elastic collision is a collision where both momentum and kinetic energy are conserved. This doesn't happen in real life macroscopic collisions, but it can be a good approximation for something like two pool balls colliding. Um, and also, there are elastic collisions on the atomic scale between atoms or molecules. Okay, an inelastic collision, which better models our real life collisions, is when momentum is conserved but kinetic energy is not. And the last one is a perfectly inelastic collision, which is when objects collide and then stick together after the collision. And now kinetic energy is not conserved, some energy goes into the objects sticking together. And in the next two examples, we'll look at perfectly inelastic collisions. In the movie Lethal Weapon, Mel Gibson's character is shot and blown through a window. Assess the plausibility of this scene by taking the buckshot that Gibson is hit with to have a mass of 50 grams and a muzzle velocity of 500 meters per second, and calculate Gibson's final velocity after the collision if his mass is approximately 80 kilograms. Okay, so I've set this up with two subscripts again. This time let's let one be Mel Gibson and two be the bullet. So we have total initial momentum equals total final momentum. And initially we have two separate terms. Mel Gibson is at rest, so his momentum will be 0, but we have P1I plus P2I equals. And after the collision, the bullet is in Mel Gibson, so they're one object now. So we just have one momentum for the system after the collision. So M1V1I, which is 0 for Mel Gibson, mass of the bullet times its initial velocity, going in the same direction as the final velocity. Then we have our total mass times the final velocity of the two objects that are now stuck together or combined. So solving for VF, we get M2V2I over the total mass, and then I can plug in the numbers here. 0.05 kilograms for the bullet, 500 meters per second over the total mass, which gives me 0.312 meters per second. And that's a very small velocity. That's much too small for someone to be fired through a window. So I would say a no to that scenario, as in not plausible. But okay, one more example for this section. A 12-gram wad of sticky clay is hurled at a 100-gram wooden block that is initially at rest on a horizontal surface. The clay sticks to the wooden block. After impact, the block slides 7.5 meters before coming to rest. If the coefficient of friction between the block and the surface is 0.250, what was the speed of the clay just before impact? All right, so I've drawn the scenario here. We have this sticky clay, number 2, and it's fired, it attaches to the block, number 1, and then that's going to have an initial velocity, but friction will slow it down within 7.5 meters so that it comes to a rest at the end of that. So first we need to use dynamics in order to find the initial velocity, or it's the initial velocity for this motion, but it will be the final velocity of the combined object after the collision. Okay, so the net force in the x direction is the total mass times A, which is negative mu k Fn. Always check, but here in the y direction the forces are 0, so Fn balances Fg. We have negative mu k total mass times g. Mass cancels on both sides, and we get the acceleration is negative mu kg. So negative 0.25 times 9.8, which gives negative 2.45 meters per second squared. Then with that, we can use 1D kinematics just to track that back and find the initial velocity after the collision. So Vf squared equals Vi squared plus 2a delta x. It's going to come to a stop. So solving for Vi, we get the root of negative 2a delta x, or the root of negative 2 times negative 2.45 meters per second squared, times 7.5 meters equals 6.06 meters per second. And with that, we can now set up conservation of momentum. Okay, I paused just so you don't have to watch me erase and write this out, but now we have the total initial momentum equals the total final momentum. And so P1I plus P2I, and then at the end, the sticky clay is attached to the block, so just one momentum term. And initially the block's at rest, so that term is 0, and I have M2V2I equals the total mass times Vf. Rearranging for V2I, we have the total mass over M2 times Vf, and plugging in the numbers here, I did leave the mass in grams because I see that the units will cancel. If you're unsure, you can always convert to kilograms, but as long as they cancel, it's not a problem. And then we end up with 56.6 meters per second as the initial velocity of that sticky clay, which is quite fast. Okay, in the next section, we'll look at conservation of momentum problems in 2D.